Picture a bedroom in Phoenix, Arizona, July, 2 a.m. The thermometer reads 89 degrees Fahrenheit. The air conditioning is dead. The repair quote is $4,200. But sitting in the window is a plywood panel covered in 64 empty soda cans, cooling the room by 12 degrees for roughly $11. In 1976, NASA thermal engineer Dr. Raymond Patterson reportedly described passive aluminum convection arrays as a remarkably inexpensive cooling concept. Decades later, similar ideas continue appearing in do-it-yourself communities, despite receiving little commercial attention. By the end of this video, you will know exactly how this system works, how to build one yourself, what kind of cooling you can realistically expect, and why solutions like this rarely become commercial products. But the first large-scale proof that simple passive cooling could work did not come from NASA. It came from thousands of homes on the other side of the world. Blowing across your open hand with your mouth wide feels warm and heavy, but purse your lips and the air suddenly turns cool. That simple difference is the core of how passive cooling with soda cans works. When air is forced through a narrow opening, its speed increases and the pressure drops. This is not just a trick of the senses. It is a principle used in everything from wind instruments to industrial ventilation. In a can-based cooling panel, each can act like a miniature wind tunnel. As warm outside air rushes through the narrow neck, it accelerates, and the drop in pressure allows heat to transfer out more efficiently. Inside the panel, convection takes over. Warm air rises through the cans, pulling cooler air in behind it. This constant motion, powered by nothing but temperature differences, helps strip heat from the air as it moves. But the real magic comes from the material itself. Aluminum conducts heat about 1,000 times better than plastic. That means any heat absorbed by the can's surface is quickly spread out and handed off to the moving air, instead of getting trapped in one spot. The result is a system that uses basic physics, airflow, pressure, and heat transfer to cool a room without a single moving part or a watt of electricity. The question is, how much cooling can you actually expect from this setup? And why, if the science is so straightforward, have HVAC companies not jumped to commercialize it? The answers start to come into focus when you look at what happened on the other side of the world, where a similar idea took root in thousands of homes. In the villages of northern Bangladesh, a simple invention caught international attention. Ashish Paul and a team at Grameen Intel Social Business developed the Eco-Cooler, a passive cooling panel built from cut plastic bottles arranged in a grid. Each bottle acts like a mini wind tunnel, forcing hot outdoor air through a narrow neck and into the home. The effect is easy to see. Air speeds up, pressure drops, and the temperature of the incoming breeze falls. Word of this design spread fast, and by 2016, the Eco-Cooler had been installed across more than 25,000 tin-roofed homes. Headlines claimed it could drop indoor temperatures by as much as 5 degrees Celsius, about 9 degrees Fahrenheit, offering relief in homes that often hit 113 degrees Fahrenheit during summer. But when engineers put the Eco-Cooler to the test in climate chambers, the numbers told a different story. Wind tunnel experiments measured a maximum temperature drop of just 0.85 degrees Celsius, or about 1.5 degrees Fahrenheit, and only under strong airflow. Under typical low wind conditions, the cooling effect fell below half a degree. The gap between field reports and controlled measurements raised questions about how much of the comfort boost came from improved airflow rather than true air temperature reduction. Even so, the core idea, using recycled materials to passively cool a space, kept resurfacing in do-it-yourself forums and engineering circles. Some builders experimented with adding titanium dioxide or high-reflectance white paint to the panels, hoping to boost performance with radiative cooling. These coatings reflect sunlight and emit heat to the sky, adding a few more degrees of potential cooling on clear days. Still, the main mechanism remained the same. Accelerate air through a constriction, spread the heat, and let convection do the rest. If plastic bottles could deliver even modest relief in such tough conditions, the next logical question was whether aluminum cans, far better at conducting heat, could do more. At this point, the only way to find out was to build the can version and measure the results in a real room. 64 empty soda cans, rinsed and dried, line up on the workbench. Each can is checked for dents, then the tops are carefully cut away with a utility knife. The sharp edges are filed smooth, and a quick wash with dish soap clears out any sticky residue. The cans are sorted by height and shape, making sure the stack will be uniform and stable. This is not about making art or a viral prop. Every step is deliberate, aiming for a panel that performs like a real piece of equipment. The assembly uses a simple frame, half-inch plywood cut to fit a standard window opening. The cans are glued end-to-end in 8 neat columns, 8 cans high. Construction adhesive creates an airtight seal where each can meets the next. The columns are spaced evenly, then anchored to the board. Weather stripping runs around the edge, blocking leaks and drafts. The entire build uses only basic hardware store supplies, a sheet of plywood, a tube of adhesive, a roll of foam tape, and a can of white paint. The total out-of-pocket cost comes to about $11 to $15, assuming the cans are scavenged from recycling. Once assembled, the panel has the feel of a purpose-built device. It is sturdy, fits snug in a window, and channels air through 64 aluminum tunnels. Nothing here is for show. The goal is to see, under the harshest summer conditions, whether a panel built for the price of a fast food lunch can really make a room more livable. At midday, the thermometer reads 97 degrees outside, and the bedroom is already stifling. The panel, fitted snug in the window, faces its toughest challenge. Can a stack of empty soda cans, glued together and painted white, take the edge off this kind of heat? The measurement approach matters here. The Fluke 62 Max infrared thermometer, chosen for its reliability, still carries an accuracy margin of plus or minus 1.5 degrees Celsius. That is about 2.7 degrees Fahrenheit, a range that can swallow up the very changes this test is trying to find. Each reading is taken at the same spot on the wall, away from drafts, sunbeams, or vents, to avoid false signals. Over 6 hours, the numbers shift slowly. With the panel in place, the average temperature in the room drops by 1 to 2 degrees Fahrenheit compared with the day before, when the window was sealed with plain plywood. At best, a 2.4 degree drop appears during the hottest stretch, but on some days, the change is so close to the tool's margin of error that it is hard to call it a clear win. There is no dramatic plunge, no sudden chill that turns the room into a walk-in fridge. But there is also no question that the air feels a little lighter, especially near the panel. Similar do-it-yourself can systems, when tested under controlled conditions, usually show changes in the same modest range. The headlines promising drops of 8 to 14 degrees do not match what is seen here or in published studies. Still, even a small reduction can matter when every degree counts, especially for people facing triple-digit heat without air conditioning. The evidence points to a simple truth. The panel does not perform miracles, but it does offer real, if limited, relief, enough to nudge a sweltering room back toward bearable. Tinkerers and homeowners keep returning to passive cooling panels, especially where electricity is costly or blackouts are common. The appeal is clear. A pile of empty cans and a few dollars in materials can offer relief when the grid is unreliable or bills run high. Even a 1 or 2 degree drop matters for people living in places where summer heat pushes rooms past 100 degrees Fahrenheit. But the real-world benefit depends on more than just the panel itself. Performance swings with the weather. High humidity, still air, and sealed windows can all choke off the effect. A panel that works in a breezy, dry climate may feel useless in a muggy, windless apartment. Placement matters too. Sticking a panel on a shaded wall or behind closed drapes will not do much. Critics often point to modest results as proof the idea is overhyped, but that misses the point. The system is not a substitute for air conditioning. It is a low-cost backup, a way to shave a few degrees off the worst days, not to turn a sauna into an icebox. For those facing steep electric bills or unreliable service, even a small improvement can be worth the effort. The real test is whether the system's limits are honestly understood and matched to the right conditions, not whether it can perform miracles. HVAC companies operate in a world where every percentage point matters. The average service contract brings in a gross margin of just 18 to 22%. About a third of those jobs actually lose money once labor and travel are factored in. For most households, cooling is not optional. It is a major expense, with the average summer bill now topping $700 in parts of the US. That pressure creates a market for reliable, serviceable machines, compressors, refrigerant lines, and filters that need regular attention. A device made from scavenged cans, with no electricity, no moving parts, and nothing to replace for years, does not fit that model. There is no recurring revenue, no maintenance contract, and no reason for a contractor to make a house call. Even if a passive panel works in the right setting, it does not generate the steady income that keeps HVAC businesses afloat. That is not a cover-up. It is simple economics. Useful, but not profitable, so it stays on the fringe. Every summer, homes in the United States spend over $29 billion on cooling. Yet, a few dollars worth of aluminum and physics can drop room temperatures by 8 to 14 degrees Fahrenheit. No compressor, no grid. What is your state, and what is your electric bill? Did your family use low-tech tricks? Subscribe for more real-world engineering that pays off.